Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 5, Lesson 2 on graphs of logarithmic functions. It's really critical that you either got an introduction to logarithmic functions already or you watched our video on Unit 5, Lesson 1 where we introduced logarithms and really talked about what they meant. We'll kind of review that a little bit here, but obviously what's going to be more important is us looking at their graphs. So let's jump right into our first exercise and take a look. Graphing logarithms. Most logarithms that are used in real world have bases that are greater than 1. In this lesson, we will explore graphs of these logarithms, including their construction, transformations, and domains and ranges. Now, as a little side, in our first lesson on logarithms, we talked about how logarithms are the inverses of exponential functions. All exponential functions are generally categorized by either having bases that are greater than 1 or bases between 0 and 1. Most of the time, though, when we graph logarithms, not use them for specific purposes, but have their graphs, we are almost always concentrating on logarithms whose bases are greater than 1. Again, most of the time. So let's take a look at exercise number 1. Consider the exponential function y equals 3 to the x and its inverse, the logarithmic function y equals log base 3 of x. Letter A. Construct a table of values for y equals 3 to the x and then use this to construct a table of values for y equals log base 3 of x. All right, well, I'd like you to do both of these without using your calculator. It should be quite quick to do this, so pause the video now and go ahead. All right, well, let's go through them, I'm going to just start with 3 to the 0, which is 1. 3 to the first is 3, and 3 to the second is 9. 3 to the minus 1 has to be 1/3, and 3 to the minus 2 therefore has to be 1/9. Let me just kind of put these in different colors so that we can really kind of keep track of them. Obviously then to do the inverse, 1/9 will give us an output of -2. 1/3 will give us an output of -1. 0 will give us an output of, sorry, I just didn't switch those at all. 1 will give us an output of 0, 3 an output of 1, and 9 an output of 2. And keep in mind, what we discussed extensively in the last lesson is that what the logarithm base 3 is giving you is the exponent that you need to raise 3 to in order to get this input. So 3 needs to be raised to the -2 to give you an input of 1/9. 3 needs to be raised to the -1 to give you an input of 1/3, etc. All right, let's take a look at letter B. Graph y equals 3 to the x and y equals log base 3 of x on the grid given. Label with equations. All right, why don't you go ahead and do that. Again, try to be as accurate as you possibly can. I know things like 1/9 and 1/3 are a little bit challenging, but take your best shot at it. All right, cool. Let's do it. Here we go, So here's our y equals 3 to the x. Here's our y equals log base 3 of x. Here's that line y equals x, and I drew these kind of diagonal lines in there to really try to help you visualize that symmetry, Any function and its inverse will be symmetric across the line y equals x, and you can really kind of see it on there with those diagonal lines drawn in, or at least I think you can. Anyhow, let's take a look at letter C. State the natural domain and range of y equals 3 to the x and y equals log base 3 of x. Now, as a little bit of a reminder, The domain of a function is all the inputs that you can substitute into the function and still get an output, Well, for any exponential function, any and all exponential functions, we can put any real number we want in for x, I can put in x equals a -1,000, x equals 1,000,000, x equals 0, it doesn't matter. So the domain is all numbers going from -infinity to +infinity. In other words, all real numbers. That's the domain of y equals 3 to the x. On the other hand, recall that y equals 3 to the x has a horizontal asymptote of the x-axis. We're going to talk about asymptotes down here a little bit. And we discussed the fact that no matter what exponent you put into 3 to the x, it can never hit 0. right? We're just like doing 3 times 3 times 3 times 3, or if the exponents are negative, we're doing 1 divided by 3, or 1 divided by 3 times 3, or 1 divided by 3 times 3 times 3, etc. So the range, right, is from 0 to infinity, right? We're not even hitting 0, right? Remember, the parentheses mean we never get there. So the range, right, is 0 and up, but never hitting 0. Now, I want you to think about what the domain and the range of y equals log base 3 of x are. There's its graph, so that should help, but at the same time, remember, the whole idea behind inverse functions is they switch the roles of inputs and outputs. So, see if you can figure that out. Well, it's really quite easy, because all we have to do is take these two things and flip-flop them. In other words, the domain of log base 3 of x is going to be 0 to infinity, and the range is going to be negative infinity to infinity. Now, this is really critical, especially the domain. That tells you that for y equals log base 3 of x, the inputs that you can put into that function are only positive numbers. They aren't even 0. You can't even put 0 in, and that kind of makes sense because what power can you raise 3 to in order to get 0? And the answer is there is no power that you can raise 3 to that will give you 0, right? And in fact, you certainly can't have any negative numbers in this domain because there's no power I can raise 3 to and get a negative number, right? I can't multiply 3 by itself repeatedly and get a negative. I can't do 1 divided by some power of 3 and get a negative. That's not going to happen either. So the domain is only positive numbers. Now the range, well, there's any y value you want because it's heading down towards negative infinity here. And yeah, it's growing very slowly here, but it is still getting larger always and heading towards positive infinity in this direction. All right, now let's talk asymptotes. Letter D. What types of asymptotes do each of the two functions have? Give both their type and equation. All right, well, we talked about asymptotes in the final lesson of unit number 4 on exponential functions. So start with that. See if you can tell me what kind of asymptote y equals 3 to the x has and what its equation is, and then hopefully that will give you a clue as to what type of asymptote its inverse has. Pause the video now. All unshifted exponential functions, all vertically unshifted exponential functions, have a horizontal asymptote of the y-axis. So for y equals 3 to the x, it's got a horizontal asymptote, specifically y equals 0, right? Y equals 0, this horizontal line, that function is getting closer and closer to, now I know it might look like it touches, but it doesn't. We talked about that extensively. So then its inverse, right? Its inverse, let me go in red here. So for y equals log base 3 of x, well, inputs become outputs, outputs become inputs, everything switches around. It has a vertical asymptote. And it's not y equals 0, it's x equals 0. Specifically, it is the y-axis. So it's getting closer and closer to the y-axis, but never hitting it. All right, let's keep going. Let me switch back to blue. Great. The common log, exercise number 2. The function y equals log base 10 of x is known as the common log and is often written without its base of 10 showing. Do the following for the function y equals log x. All right, pause just for a moment. Logarithms are actually a relatively new invention in mathematics. I think that they were invented sometime in the 1600s. When they were invented, the only base that they used back then was the log base 10. So in fact, they only had one logarithm, it was this thing, and they didn't feel the need to write the little 10 down there because that was the only logarithm there was. It eventually became known as the common log because it was the one that was most commonly used, and you will still find it written all over the place without the 10 showing, including, and probably, on state assessments. So it's important, right, that you know, even if you've got something like the Inspire that will always force you to put a base in, it's important to know that if the base is not written under the word log, that it is base 10. All right, let's take a look at letter A. Use your calculator to sketch its graph on the axes. Okay, so let's put this thing in. And again, it's a little bit unfortunate because we really do have to put in that base 10. So I'm going to hit my log button. All right, I'm going to put a base of 10 in, and then I'm going to put x right there. And there it is. Now granted, you know, I have a slightly different scale on here, right? I'm not showing all of this over here. So let's get that scale in, right? We've got -2 to 10 and -5 to 5. So I'm going to go in here into my Windows settings, -2 to 10 and -5 to 5. And there we go, right? And I don't have to make a perfect sketch. I'm going to just kind of do something like this. Put arrows on the two ends indicating that it's heading down towards infinity in this direction, and it's heading to the right and sort of upwards in that direction. Okay. Letter B. Why does it make sense that this function continues to have a vertical asymptote of x equals 0? So I claim that this thing still has a vertical asymptote of x equals 0, which is just the name that, you know, which is the equation of the y-axis. Pause the video now and see if you can think about why that would be. Well, it's kind of cool. And it all goes back to the inverse relationship between exponential and logarithmic functions, you see. Y equals 10 to the x has a horizontal asymptote of y equals 0. So y equals log of x must have a vertical asymptote of x equals 0. And it's so cool because inverses always do that. You know, if one function had a y-intercept of 7, the other function would have an x-intercept of 7. One of them has a horizontal asymptote of y equals 8, the other one would have to have a vertical asymptote of x equals 8. That's just the way inverses are. So let's take a look at this final little piece and then we'll move on to the next example. Logarithmic function graphs. A basic logarithmic function of the form y equals log base b of x, where b is greater than 1, has an increasing graph with a vertical asymptote of the y-axis, a vertical asymptote of x equals 0. All right, let's take a look. Let's talk about the intercepts of basic logarithmic functions, right? Y-intercepts, x-intercepts, things like that, because that's kind of important to think about. Let's take a look at exercise number 3. Consider the basic logarithmic function f of x equals log base b of x, where b is greater than 1. Okay, so in other words, I'm not even telling you what the base is anymore. I'm saying that whatever we're going to answer right here is going to be true about whether we're talking about log base 2 of x, log base 10 of x, log base 18 of x, log base 2.712 of x, you know, any of those. So let's take a look at letter A. Explain why f of 0 is undefined, right? Well, why don't you try to figure out what f of 0 is, and maybe that'll give you a clue as to why it must be undefined. Well, let's take a look, right? F of 0 is going to be the log base b of 0. Now, how do we think about log base b of 0? Well, let me just put like something here, like n, right, for number, right? Now, what that's going to give me is the power I would have to raise b to in order to get 0. But keep in mind, right, b is a number that's greater than 1. And there is no way that you can take a number greater than 1, or even a number less than 1, or any number actually that's not 0, and raise it to a power and get 0, right? There is no exponent you can raise b to get 0. There is no exponent you can raise b to and get 0. Now, that's kind of cool because that tells us something about the graph of this function, letter b. What does a tell you about the graph of f of x? This is kind of awesome, right? Pause the video now and see if you can tell me. Well, it tells me it has no y-intercept, right? F of 0, regardless of what kind of function we're talking about, always gives you the y-intercept. And if f of 0 is undefined, that means that the function has no y-intercept. So a general logarithmic function won't have a y-intercept. Just no y-intercept. All right, let's take a look at C. What is the value of f of 1? All right, well, same thing. See if you can figure that out. Okay, well, let's do it just like we did before, right? F of 1 is going to be the log base b of 1. So again, we ask ourselves a very simple question. This is equal to some number, right? And that number is going to be what we have to raise b to in order to get the number 1. Well, this is kind of cool, right? Because we know that any number that's not 0, any non-zero number raised to the 0 power will be equal to 1, right? So, since b to the 0 is always equal to 1, n must be 0. F of 1 is always 0, so the log base 10 of 1 is 0, the log base 2 of 1 is 0, the log base 50,000 of 1 is 0, because any base raised to the 0 power gives me the number 1. And what does that tell you in letter D? What does C tell you about the graph of f of x? Well, it tells us that the point 1, 0 lies on it, so it has an x-intercept at x equals 1. Every logarithmic function, every basic y equals log base b of x passes through the point 1, 0. So every logarithmic function, as long as the base is greater than 1, which is most of the time what we're going to deal with when we deal with graphs of logarithms, has a vertical asymptote of the y-axis, but never hits the y-axis because it doesn't have a y-intercept, it always passes through the point 1, 0. Always, always, always. It doesn't matter what the base is. All right? So let's test this a little bit in the next problem. Exercise number 4. Given what you saw in exercise number 3 for a general logarithm, sketch a graph of y equals log base 7 of x without the use of your calculator. Mark the function's x-intercept and label one additional point. Verify using your calculator. All right, well, let's do this together, okay? What we just said is that for any given base, it doesn't matter, and let me write this a little bit bigger. For any given base, we know that the function will always be increasing as long as the base is greater than 1. It will always pass through the point 1, 0, and it's going to look something like that. Right? That's what that logarithmic graph is going to look like. Now, it does say give one additional point, right? There's our x-intercept at 1, 0. Maybe I'll just write that down. But it's kind of like, well, what's one additional convenient point? Well, Think about that, right? What value of x could I put in here that would make it very easy to answer the question 7 raised to the what gives me x? Well, what's certainly true is if I put x equals 7 in, y would be the log base 7 of 7. What do I have to raise 7 to in order to get 7? Well, it would have to be to the first power. So a very convenient point on any logarithm will be an input that's equal to the base, right? Because if I'm asking what's the log base 7 of 7, the answer is 1. What's the log base 12 of 12? That's 1, right? So one additional point that is very nice to put on this is the point 7, 1. All right. And let's actually put it in our calculator to verify. Let's go ahead and do that. I'm going to just, I think, modify this one. So I can just kind of go up, and it's great because all I have to do is come in here and put a 7 there instead. And there's my graph, and it basically looks almost the same. It's a little bit hard to look at it here, but it is going through 1. In fact, let me do something really quick. I'm going to go into my window and my window settings. Right now, my x scale is going by 1/2. I'd like it to just go by 1s. All right, that'll make it a little bit easier to see things. You can now see much more simply that the function is going through the point 1, 0. It's a little bit harder to see the point 7, 1, but 1, 2, 3, 4, 5, 6, 7, that would be right about there. Not that that particularly helped, but it would be right about there on our graph. Now I'm getting multi-select. I don't even know what that means. But notice again, you know, when I changed it from log base 10 to log base 7, the graph essentially looked exactly the same. Here we see that vertical asymptote again. It's getting so close to the y-axis that we really almost can't see the difference between the two. But if we sort of zoomed in on this portion of the graph in here, we'd still see a sliver of daylight between the function and the y-axis. A vertical asymptote. All right. Now, let's take a look at exercise number 5. Find the larger solution to the equation shown below. Provide a sketch on the axes to justify your answer. Round to the nearest hundredth. All right, so we're trying to solve the equation log base 7 of x equals x minus 2. It seems like because they're asking me for the larger solution, there's probably going to be 2 solutions, right? And we want the bigger one. See if you can figure out how to solve that problem graphically. Well, keep in mind, right, since we don't really have any equation solving techniques that we can use with logarithms right now, the only way to really do this particular problem is to graph this in one equation, graph that in another equation, and find out where they intersect. Of course, we already have the one graphed. It's sitting right there. Now all I have to do is put the second graph into my calculator, and that was y equals x minus 2. That is definitely not what I wanted. Knew it was going to happen eventually. Let me expand that and bring this back out and bring this over. Fantastic. Stop that. Stop that. Okay, there we go. Wow, that was a lot of work just to get it all the way back to x minus 2. There's that second function. Yay. Now, it's kind of interesting, right? There really are 2 intersection points. One of them is down here, very, very, very close to the y-axis. It's not right at the y-axis, but it's really close to it. The larger one, the one that's going to be easier to see, is right out here. And of course, we can find that by going into Analyze My Graph, use my intersection command. I'm going to bring that right over here, hit Enter, bring it over here, hit Enter. There's my intersection point. Let me bring it up here so that it's easier to see. 2.463 on the x, 0.463 on the y. Let me just draw a nice graph of that. Hopefully I can get back into here without it all going downhill. Right, so my graph is going to look something like this. I would label this y equals log base 3 of x. Let me go red for the other one just to give us a nice contrast. Maybe I'd get something like this, right? Y equals x minus 2. Maybe I will then do this. We have an intersection point. That was at 2.46 comma 0.46, and therefore I can say that the larger solution to the nearest hundredth is x equals 2.46. All right. One expectation, one fluency expectation that at least you have in New York State is that you'll be able to solve basically almost any equation they throw at you graphically by graphing the left-hand side and the right-hand side of the equation. That can be a little bit confusing, obviously, because a lot of your equation solving techniques that you're going to learn in Algebra 2 don't require the use of a graphing calculator. So if you ever see one that they throw at you and you're like, well, I don't know how to solve that algebraically, consider graphing the left and the right-hand side and just finding the intersection value. All right, let's take a look at one last problem. Horizontal shifts of logarithms. It is common to horizontally shift logarithmic functions so that their vertical asymptote is at a location other than the y-axis, right? Without horizontally shifting, we're always going to have that vertical asymptote of the y-axis. The shifting follows patterns that you saw in Algebra 1 that are a bit counterintuitive, but I'm kind of hoping that this will remind us of those patterns. Exercise number 6. For each logarithmic function shown, graph in your calculator and identify the vertical line that is the function's vertical asymptote. Use the trace command to verify. Draw a sketch to illustrate. All right, cool. So again, just keep in mind, let me switch back over to blue. Keep in mind that if I had, let's say, this function, y equals just log base 2 of x, right? That thing would have a vertical asymptote of the y-axis. But now I've subtracted 3 from the x value first, and so that's going to shift this some way. It's either going to shift it to the right 3 units or to the left 3 units. Let's see if we can remember which by graphing it. Let's take a look. All right, so I'm going to come back into my graphing calculator and hope like mad. Actually, I'm just going to add another page in. I'll add another graph. Yeah, sure. That'll work for me. No, I did it again. Okay, I can't get that thing anywhere near the ceiling. All right, the ceiling, as if it's the ceiling. So log base 2 of x minus 3. And take a look at that. All right. Now, let me open it up a little bit. I don't have anything going on over here, but I got a lot going on over here. So let me just for a second go into my window settings. I think I'm going to just keep a little bit in terms of negative x values, maybe expand that a little bit more. I'll keep the y values of where they are, and there we go. Now, it definitely has been shifted to the right, all right, and I claim it's been shifted to the right 3 units because we have x minus 3 there. But what's kind of cool is one of the things that you can do in your graphing calculators is you can do what's called a trace. That's option 5. And if you do a graph trace, what happens is you can literally move your cursor along the graph, hopefully, and what you can see is how the points along the graph change. It's probably going to work better for your calculator than mine, but look at what's happening. As I move along, right, my x values are getting closer and closer to 3, right? 3.1, the graph is getting more and more vertical, and if I go one more, it says 3 undefined and then throws in that dashed vertical line that is the vertical asymptote. All right, and it's really kind of cool, right? As I get closer and closer to 3, the curve more and more wants to bend and go vertical and wants to act like a non-function at that point. Huge changes in y for very small changes in x. All right, now how am I going to sketch this thing? Real simple, full screen. I just want to make a little sketch that looks like this. I'm going to go 1, 2, 3. I'm going to put a dashed line in for my vertical asymptote, and I'm just going to do this. All right, with a vertical asymptote of x equals 3. All right, what I'd like you to do is now play around with letter B. Now, it really doesn't particularly matter whether it's log base 2 or log base 3 or log base 10, the common log. If I put this one in and I compared it to log base 3 of x, what I would see is that it was shifted 4 units to the left. And in fact, what that would then look like if I did a generic sketch of it would be 1, 2, 3, 4. we'd have a vertical asymptote of x equals -4. Let me just label the x and the y axes on both of these for due diligence. And then we would have a graph that kind of looked like that. All right. Now, if this feels a little bit familiar to you, I hope it does. In the last unit, we looked at vertically shifting exponential functions so that they had different horizontal asymptotes. Notice we vertically shifted exponential functions and we got different horizontal asymptotes. We are now horizontally shifting their inverses, logarithmic functions, in order to get different vertical asymptotes. All right. The thing that's of course tricky about horizontal shifting is it sort of works in the opposite direction of what you'd expect, i.e. when you subtract from x, you shift the graph to the right, and when you add to x, you shift the graph to the left. Okay, let's summarize. So today we looked at graphs of logarithmic functions. And of course, to produce a graph of a logarithmic function, which is the inverse of an exponential function, you simply have to switch the x and the y coordinates in graph. Our graphing calculator, so thankfully, will have a generic logarithm button on it. So if we're asked to graph y equals base whatever of x, we can always put that into our calculator, generate a table of values, or just generate a sketch of the function. Now, we saw a lot of different things with the general logarithmic function and its graph, including the fact that it will always have a vertical asymptote. If it hasn't been shifted, that vertical asymptote will be the y-axis, and in fact, it won't even have a y-intercept because it can't hit the y-axis. Again, if we're talking about a basic logarithmic function, they will all have x-intercepts at the point 1, 0, and you can always find another point on the graph by simply taking the base and substituting it into the function itself. We'll work on and off with more logarithmic graphs as this unit progresses. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.